Welcome back to the deep dive. Today we're going into a really technical but absolutely crucial topic, large language models. Specifically, we're looking at this single kind of radical idea. How do we make LLMs not just think, but think better? We're looking at sources that tackle these massive challenges like competitive math problems, and our mission really is to find the shortcut to genuine cognitive efficiency.
It's a fascinating area because the source material really points out that when you look at these big models, GPT-4o, DeepSeek, they're incredibly powerful. But their method for solving the really hard problems is often, well, it's brute force.
Right.
They're using things like chain of thought or tree of thoughts, which are just these massively long trial and error sequences.
So if you're trying to solve a complex multi-step problem, those methods basically turn the whole thing into this huge, sprawling search for the right answer.
Exactly.
They're just wading through this enormous search space. It must be so computationally expensive.
It is. And that inefficiency is exactly what this new framework, ReasonFlux, is designed to fix. The core idea is hierarchical LLM reasoning via scaling thought templates. It's all about optimizing the process of thinking itself.
Okay, so instead of brute force, it's giving the LLM a strategy. A high-level plan.
A structured plan, yes.
All right, let's unpack this then. Because on one hand, you have these proprietary models from the giants, and on the other, you have ReasonFlux 32B. And here's the kicker. It used an open-source base model and was trained with only 8 GPUs.
Just 8.
Yet it somehow leapfrogged those giants, especially OpenAI's O1 preview, on these really tough math benchmarks. So our mission today is to figure out the 3 core innovations that made that happen.
To really get it, we have to start with why the current methods fall short. Why brute force thinking fails when the problems get, really competitive. Right now, models use 2 main approaches. There's deliberate search, like tree of thoughts or graph of thoughts, where they explore tons of different paths. And then there are reward model-guided methods, things like Monte Carlo tree search, MCTS.
So let's use an analogy. If solving a math problem is like finding your way through a giant maze, these existing methods are basically trying every single turn, every corridor, and then backtracking when they hit a dead end, just hoping they eventually stumble out.
That's a perfect visual for it, and it highlights the huge computational cost. But the bigger problem really is generalization.
What do you mean?
Well, they rely on search strategies that a human has to design, or on these very, very specific rewards for each little step.
So they can't see the big picture.
Exactly. They can't capture the high-level, abstract thinking that a human expert uses. They're good tacticians, but they're terrible strategists.
And the sources mention that people have tried to fix this before, right? With things like buffer of thought.
They have. It was a step in the right direction, but it just didn't scale. If a problem needed you to combine, say, algebra and geometry, the system couldn't stitch those different strategies together effectively.
So that failure, that's what sets the stage for ReasonFlux's first big innovation.
Precisely. The construction of the structured template library. This is the foundation for everything else.
A structured template library. That sounds like more than just a big database of answers. You called it a toolkit.
It is a toolkit, a very, very curated one. The researchers built a library of around 500 high-level thought templates.
500?
And they didn't just pull these out of thin air. They analyzed thousands of solutions to really complex math problems, from the math data set, from Chinese high school competitions. They basically distilled the common strategies that human experts use over and over again.
I wish I had that in high school. So what makes these templates structured? Why isn't this just a big block of text that the model has to read? Because that sounds a lot like RAG, retrieval augmented generation, and we know that can have problems with really complex questions.
That's the critical distinction. The structure is what gets around those RE issues. It lets the model retrieve a strategy based on its metadata, not just, some keyword that happens to be nearby. Each template is broken down into these key components. First, a concise name, something like a square root of r squared minus x squared type trigonometric substitution. Very specific.
Got it.
Then you have tags for quick searching, substitution method, irrational function optimization, things like that. Then a description that explains the principle. So for our example, it would say, use this when you see this specific radical form and when x is less than or equal to r.
It's giving it the exact conditions.
The exact conditions. And finally, a clear step-by-step list of application steps.
So the model isn't just getting some vaguely related paragraph, it's getting a fully structured algorithm.
Yes.
It's almost like a function in a programming language. It tells the model exactly what to do, what the inputs are, what the output should look like.
That is a powerful analogy. It uses that metadata to filter and find the exact strategic tool it needs, which just shrinks the search space from the very beginning. It's so much more efficient.
Okay, so we've built this amazing tool chest, the template library. But a good builder doesn't just grab tools at random, they have a plan. And that gets us to the next two innovations, the master plan and the execution.
Right. Innovation 2 is what they call the navigator. This involves training the main ReasonFlux LLM using hierarchical reinforcement learning, or HRL. The whole goal is to make this LLM a pure, high-level strategic planner.
So wait, it's not actually generating the final answer itself.
Not at this stage. It's optimizing the abstract sequence of steps. They call it the thought template trajectory.
This is where it gets really interesting for me. The LLM is acting like an expert strategist before doing any math. It's planning the sequence. Use template A, then template B, then do a check. That is completely different from just generating one long chain of calculations.
Completely different. By planning at that high abstract level, the search space for the planner becomes much, much simpler. And once that plan, that trajectory is set, we move to innovation 3.
Which is the adaptive inference system.
Exactly, the new inference scaling system.
So walk us through that flow. How does it work in practice?
It's a 3-stage loop, really.
Sure.
Stage 1, analyze and configure. The ReasonFlux Navigator looks at the problem and puts together what it thinks is the optimal trajectory, just a sequence of template names.
Okay, the plan.
Then stage 2, retrieve and instantiate. It grabs the first template from the library and hands it off to a totally separate model,
The different model.
a different specialized model called the inference LLM.
So the inference LLM is the worker bee, the execution engine.
Correct. It takes that abstract template from the navigator and instantiates it. It fills in the specific details from the problem, does the calculation, and solves that one subproblem.
And then comes the part that makes it dynamic, right? The feedback loop.
Absolutely. The result from that subproblem gets sent straight back to the ReasonFlux Navigator for evaluation. If the result looks good, it moves to the next step in its plan. But if the result looks messy or illogical, say an intermediate step produces a non-real number when it shouldn't,
It can change the plan.
it can dynamically refine the rest of the trajectory, it might adjust the next few steps, or even scrap that template entirely and try a different high-level approach.
That is exactly how a human expert works. You don't just stick to a bad plan. You check your work as you go.
Right.
And if you see you're heading for a dead end, you take a step back and pick a whole new strategy.
And that's why it's so much more efficient. The system is optimizing the overall thought process, not just agonizing over every single token in a long, rigid chain. It allows for strategic course correction.
Okay, so a better tool chest, a better planning process. Let's get to the results because this is where the payoff is for you, the listener. We're comparing this 32 billion parameter model against frontier models that are way, way larger.
And the performance gap is, well, it's striking, especially on these benchmarks that require really deep, multi-step reasoning. We're looking at pass at 1 accuracy, which means getting it right on the very first try.
The gold standard.
The gold standard. On the math benchmark, ReasonFlux 32B hit 91.2% accuracy. That beats OpenAI's O1 preview, which scored 85.5%. That's a 6.7% jump.
And nearly 7% margin on a benchmark that hard is huge. But it gets even crazier with the AIM 2024 benchmark, right? That's for U.S. Math Olympiad qualifiers.
That's where the strategic planning really pays off. On AIM 2024, ReasonFlux 32B got 56.7% accuracy.
And how does that compare?
It surpassed O1 Preview, which got 44.6% by a massive 27% margin, and it beat DeepSeek V3 by an incredible 45%.
Wow.
And get this, it matched the performance of OpenAI's proprietary O1 mini model on this test.
And I have to keep bringing it back to the resources. This state-of-the-art performance, beating these massive proprietary models, was done with an open source base and just 8 A100 GPUs.
It really proves that a smarter architecture can trump sheer scale.
It's not just about a bigger brain.
It's about a better playbook. And the generalization data backs this up. On other tests, like Olympiad Bench, it scored 63.3%, beating DeepSeek V3 by 14%. The templates capture these universal math principles that just work across different types of problems.
Which brings us to this core technical advantage, the exploration-exploitation trade-off. We know the old methods are expensive. How does this template-driven approach change the cost?
This is key. ReasonFlux achieves a far superior exploration-exploitation trade-off. The cost metric they used was basically the number of attempts or interactions the model needed to get the right answer. Exploration is, trying new paths. Exploitation is using a strategy, works.
So a high exploration cost means it's just wasting time going down dead ends.
Wasting a lot of time. The research tracked this cost across 4 difficulty levels of AIM problems, and the results were dramatic. For methods like MCTS and best of N, the exploration cost just shot up as the problems got harder. MCTS's cost went all the way up to 42.8 on the hardest level.
Wait, 42.8, so it needed almost 43 separate attempts to find the solution.
43 different branches of calculation. It's an enormous amount of wasted computation.
Wow.
In contrast, ReasonFlux's cost stayed low and stable across all difficulty levels. And the reason is the template library. It acts as a filter from the very beginning. It stops the model from even considering paths that a human expert would instantly know are dead ends. The navigator can immediately exploit high-quality, proven strategies instead of randomly exploring.
It's like a resource multiplier. You're not just making the model better, you're making it smarter with the resources it has.
Right, and the sources show that even smaller base models, when you augment them with these templates, get huge accuracy boosts, sometimes over 20%.
So a smaller model with the ReasonFlux playbook can beat a much larger model without one.
That's the takeaway. The quality of the mental playbook matters more than the raw size of the brain.
Fantastic. So let's wrap this up. What does this all mean for you, the listener, who maybe isn't solving Olympiad math problems every day? The core takeaway here is that ReasonFlux shows that optimizing how an LLM thinks, with this structured, hierarchical guidance, is just way more effective than just making models bigger or generating longer and longer chains of text.
It's about getting the model to behave more like a human expert, breaking a problem down, picking the right tools, and, crucially, adjusting the plan when something isn't working. It's a move away from just prediction and towards real strategic intelligence.
So what does this all mean for the future? I mean, if these structured, high-level templates let an LLM master complex math with this kind of efficiency, imagine applying that same structured thinking framework to other fields. Think about medical diagnosis. The templates could be diagnostic algorithms or treatment protocols, or, high-level legal analysis where the templates are different legal precedents and procedural strategies.
Go to strategic planning, where there are operational playbooks.
Exactly. What kind of structured templates would we need to build for those fields to see the same kind of leap in accuracy and efficiency? That's something for you to mull over until our next deep dive.